Welcome back to our Starknet Basecamp. Today we're going to be going over the lesson on creating a simple DeFi vault on Starknet. So what are the learning objectives for today? So at the end of this class, you should be able to gain hands-on experience in building a simple DeFi vault on Starknet, and also develop basic smart contract development and interaction skills on Starknet. So we're going to go straight to the hands-on building. Alright, so let's get started on the simple DeFi vault. I'm going to move to a temp folder, but you can move to whatever folder you want your program to be built in. And we're going to use Scarab, which is the package manager for Cairo. So we do a Scarab new and the name of the program. So we just call it simple vault, and it's going to ask us to choose either Starknet Foundry or Cairo test. So in this case, because we are building a Starknet contract, we can use a Starknet Foundry. Going to install with the latest version, and then we can open it with our favorite test editor. So I'm going to use Cursor and simple DeFi vaults, which will be right. So we have it installed. If you check scarab.toml for our dependencies, you're going to see the name of the package, the version, the edition of the prelude, and the dependency we have right now is Starknet. So for ease, we're going to be using another package called Open Zeppelin token. So I'm going to just do a Scarab add. Scarab add Open Zeppelin token. The latest version is 1.0 as of today, but it can change. But if we do this, we have the dependency. So these are good. This is going to be the two dependencies that we're going to use for the contract. So we have this all set up. If we now go to our source directory and lib, this is where we're going to write the whole contract. You'll see the example here. So we're going to delete this. Just for ease, I will just rename. So I'll just take this one out, take the comment, and we have an interface. So this interface is just a blueprint of the entry points of the contract. So this will be like where we define a function with no implementations for the contract. So in this case, I can just call it I would take this out, I simple vote, and then we'll define the entry point. Find the entry point of the simple DeFi vote contract. So I can just also take this one out. And for this case, we will have 4 entry points. The first one will be deposit. I can do a tab complete, but this is still not correct, so I will just correct it. In Cairo, if we have a ref self, that means this is going to be a read contract. So we're gonna a write contract, my bad. So ref self and then the T contract states, and so the amount as U256. This one is fine. We don't need it to return anything, so we just leave it as this. So in the other one, we can have a withdraw. So the same thing, because we're going to be modifying the state of the contract, we can also use ref self and T contract state, and then shares, and we can say U256 also. And also, we don't need it to return anything in this case, so we are good here. And in this, we're going to have a read. So we can use this to get user balance. So we can call it get user balance. So we can call it get user balance. And this one is a read. So we don't need to use a ref. So we just need to use this, and we'll take a snapshot at the contract state and the account, which is going to be a contract address. So we'll say account contract address. That's the type. And in this case, we're going to be returning, I did not spell the address correctly, so I'll do ADDRESS. And we're going to be returning a U256. We'll see that this is still a squiggly line, and the reason is because we don't have the type definition here. So type not found. So for us to install the type or to import the type from the standard Starknet library, so we have Starknet installed, in the dependency, we can use a use Starknet and the name, which is contract address. So this should take out the error in this space. We're going to leave this one for now. We can just modify. We just take out this, and this should be fine. We're going to take out this to implementation because the contract has actually changed, so we can take this one out. And yeah, it's going to be, this doesn't exist, so we can use the super and simple vote. So I simple vote. It's still going to have a squiggly line. In this case, we can also simple vote implementation. So this will be the implementation block of the simple vote. Again, there's errors here because we don't have the definition. So we have 3. Actually, we would have 4 entry points, but let's just function deposits. Okay, so we are implementing all the traits here. So f in deposit will have a ref self, and then contract state, and then amount U256. And we will not necessarily implement the functions for now. We just have it like empty. We can do the same for here because we know this. And in this case, we can have this type not found. Okay, now it's still trying to read the contract, and the contract type is not found because it's not on the scope. So what we can do is import it here. So in this case, I'm going to use a use super and then contract address because and the main reason here is because we have the contract address here. So we, with the super, we're going down one scope, and it's going to be in this space, so we can get the contract address. So at least for now, we have a rather sane contract. I'll try to explain this again. I'll try to go over what we've defined here in this contract. So far, we imported the contract address, so the contract address type, and we defined a Starknet interface here. So again, how you define a Starknet contract interface is using this attribute, Starknet interface, and then trait of I simple vote, T contract state. We're using this generic here because again, it can be anything. So we have the T contract state, and it could have been T state, it can be T, just any generic will be fine. And then in there, we define the functions. So this interface can be used to implement this. And if we want to call the contract or interact with the contract from an external contract, we can use this interface. And declaring this interface also automatically generates the contract dispatcher and the dispatcher trait. So once you have this, you can use the contract dispatcher, and we're going to show you an example when we import OpenZeppelin. So I'm going to do that next. So I can use a use OpenZeppelin token. That's the ERC20, and yeah, we're going to get the OpenZeppelin ERC20 interface, and then we want the ERC20 dispatcher and ERC20 dispatcher traits. And then we can just tap complete this. And we're going to use this to define the storage of our vote. Right? So again, every Starknet contract needs a vote. So in this case, we would have 3 storage. We have the token. We call it ERC20 dispatcher, which we just imported from OpenZeppelin. We have a total supply. We can call it a U256, and we can have a balance of BAL balance off, and we have it to a map. So if we want to map the balance off to a contract address and the value, so we can do this. But with this, we'll still get an error because we need to import the trait here. So we can import it from the Starknet storage. So we'll say map, and we need the storage map read access. So storage map read access, and storage map pointer. We need a storage map write access. So storage 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 map write access. And I think we took out the storage read access, so we're gonna import that back too. So will be storage pointer. Is it read or write? Write. We need a write. Oh, we need a read access. So we import. These are all the importations we're gonna need to interact with a simple vote. So in this case, I'm just going to change this to a simple vote. Just bear with me. Yes, so simple vote. And we can have a constructor. So we set a constructor for when. So to get a constructor, we need this. So we just define it as a constructor. And we can do a fn constructor, and then as a ref self, because we're going to modify the storage in this case. So contract states, we're going to modify the contract state and the token. So in this case, it's going to be a contract address. So we will need to know, the address of the token we're going to use for the vote. So once this contract is deployed, this constructor will run for once at the deployment time, and we can set this, token that we're going to be using for the vote. In this case, we can do a self token write, and then we can use a IERC20 dispatcher, which would take in a contract address and a token. And yeah, this is going on all right. So next thing, we can have like our internal functions that we need. We can scope them into a private function, and the way you can do this, we can have this here. We can say generate trait. And we create an implementation for the private function. So we just say private functions of private, and this could be any name, right? So just convention, we can call it, private function. And this is where all the private functions we're going to use in our contract will be stored. I'm using Copilot, and it's suggesting, that we use this. So I'm just going to go with it and edit it if it's wrong. So in this case, we have a function mint, and this underscore is just convention, right? And we're going to modify the contract state. So it's ref self contract state and the amount. Give me a second. We're going to modify this. So I think we need more than this. So we need the address of the person we are minting this to. So we'll do it to contract address and the shares. Okay, I don't know how to spell address for the love of me, so I think this is the spelling of address. And in this case, we are minting shares to the user, so we can just call it shares in this case. So we can say shares 256, and this is, yeah, this should be enough. And then in this case, we can read. Okay, we're going to be writing to it. So give me a second. I can just sometimes we don't need to use open Copilot because it hallucinates. But in this case, yeah. So we can just do this. So we can get self dot total supply read plus share. So what is going on here is self.total supply dot write. So we're writing to the total supply here, right? So we want to add number of shares that we are minting. So total supply, we want to read the value of the total supply and then add number of shares we're minting here. And then we can also increase the balance of, so self write, and then the 2 that we're getting here. So who are we increasing this to? So self dot balance of. Okay, this is correct. So again, we are increasing the balance of the user. So this is the map, so the contract address and the shares that we are increasing. So in this case, we are minting the shares to this user. And then we can look at the burn too. We will do the same thing just in reverse, right? So if we're burning, we're reducing the shares of the user. So I will just copy this and I will paste it here. And I'll change the name. So it's not supposed to be mint, it's going to be born. And in this case, we're just reducing the number. So negative. So again, we are reducing the total supply and the balance off in this case. So we're minting and we are burning. So these private functions should look good now. So the next thing is the actual implementation of the DeFi vote. So again, we are using the ABI embed v0. So we're saying all the functions in here will be public. And in this case, we're using generate traits. And if we wanted this to be public, we would have marked it up here that this should be public. But in this case, we are not, we don't have any public function here. So everything is private and these ones are public. Okay. Right. Looking at these functions, maybe I will just implement this one first because it's the easiest. So to get user balance, we just need to do a self.balance_of.read, literally this, and we should be able to get a user balance. Next will be deposit and withdraw, which should take a little bit more time. So for the deposit, we need to know the caller and the contract address. So we need some functions. We need to import more functions from the Starknet library. So we're going to do that. So in this case, we're going to use Starknet. And then we need to get caller address. So if we use this function, we should be able to get the caller's address. And we will need that for the deposit and withdraw, and then we get contract address. So these two library functions would help us. So we'll go back to the deposit. So the first thing is we want to know the caller address. So we'll do a let caller. Okay, I cannot spell. Equals get caller address. So this should be fine. So next thing is we want to know the address of this contract. So we can do this get contract address. So we just auto complete this. This should also be fine. So in this case, we can get share. So because the share would change, so we can do a mute shares equals 0. And then we have a conditional here. So if self.total supply is 0, the shares will be the amount, and else we can do this. So yeah, so if the total supply is 0, so the shares is the amount. So this is the initial share minted, but else if there's already existing shares, we need to calculate number of shares to mint to the user. So in this case, we say shares equals amount times total supply read All right, so shares equals this, so we can just put this first in its own curly brace, and self.token.read. No, in this case, we need to know the balance of this user, so we can do a balance of these. So we want to know, the balance of the contract in this case, and then we can do I think this should be fine. This should return a U256, but let me just check. Yeah, this returns a U256, so this should be fine. And again, this is just the interface of the IERC20 token. You can take a look. This is what we imported from OpenZeppelin. So we'll go back here, and this should be fine. So now next thing, we can just call the mint. So private function mint. Yes, this works. I think we have to do ref self. See what's going on. Expected variable constant found implementation. See, is there anything wrong here? Okay, yeah, no, this is fine. Okay, so it was just my linter. So we just go again, and what we're gonna do is do a self.token.read dot transfer from, then would have this. Yes, this should work. Is it amount of shares? Yeah, no, this should work. Okay, so this will be the implementation of the deposit. So let's also implement the withdrawal. So okay, so this is implementation of depositing to the contract. So next will be withdrawal. So in this case, we also need to know the color, and let's just find this, and this should work. Okay, so autocomplete gave us the solution here, so we are fine. And yeah, save this, and this should be our simple implementation of DeFi Vault. So next step is, let's just run a lint. So we have, if you check a scarab-help, you see some comments here. So I like to run the format and lint. So in this case, you just kind of make sure that everything is okay. So if we do a scarab fmt, so this should kind of format it correctly. I think it was already formatted correctly. And if we do a lint, we should also know that this has no issue. Okay, so everything looks fine. So next thing is going to be okay, so we do a scarab build, and it takes a while to kind of compile this and build the contract, but this should be ready in a couple of seconds. So we just wait, and I will just skip through it to make it faster. But okay, so it's built. So now next thing, we can use Starknet, and you should have installed Starknet in the past. It's a command line utility. If you've not installed it, there's a tutorial on setting up your development environment, and it has this. So we can just do a Starknet declare, and lately I don't know how to spell GECL. Yeah, this should work. And then we say target, because again, once we built it, created a target for us. So target dev, and it's going to be simple DeFi, this one, simple Vault contract, not the artifact, just the contract class. So if we run this, because we did not specify it's going to use it, so we're gonna be fine. So I'll just do a T, and okay, so I'll just put in my password. Okay, so we created a contract class hash for this. So the next thing is to deploy it. So for us to deploy it, we need a token address. So the token address of the token we're going to use. In our case, I can go to our Explorer and find the address of either it or Starknet contract. So just give me a second to pull up that. All right, so this is our Explorer. This is where we're going to find the contract class hash that we're going to use. So in this case, I'm just going to connect my Sepolia address, and I'm going to find the Starknet token. I'm just using this to show you how to kind of explore the Explorer. So in this case, I just searched my contract name. If I check this, I should be able to see the tokens I have. So I will just copy the token address for Stark, or again, we can copy the one for it. Let's just copy the one for it. So I'll copy the one for it, and then I'll do you know what, I'll have to copy it twice. I'll do a stack lie deploy, the class hash that was just declared. So again, how a Starknet contract works in the deployment, you have to first declare it. It creates like a blueprint that you can deploy instance of from. So the class hash in this case will be the blueprint, and now we're going to use the class hash to deploy an instance of the class of the contract. So we have the class hash, and then we need to put the arguments for our constructor. So again, it's going to be, I'll copy this address and I'll paste it here. So if I do this, it will ask for my password again. So all right, so the contract is deployed, and you can just copy this, and I'll go check it on the Explorer. And sometimes it takes a few seconds for it to show up. In this case, it was fast. So we have this. So if we check the read, we'll see that we have get user balance, and this is the right functions here. So you will see something. So if we connect it here, I'll use my agent, and I try to deposit. I'm going to get an error. So let's just try to deposit 10. And this is not 10.8 because again it's unit of 8. So it's going to give me this error. It's failed, and this is because I've not approved the contract to spend money. Because if you look at the contract implementation, we have a transfer from here. So we're trying to transfer from the caller to the account, so the contract address, the amount that we specified, right? But the caller or the contract does not have access to spend money from the caller. So we will go, give me a second. So we'll take this. I'll just open a new instance of Stark Scan, and I will approve the contract to be able to spend. So I'm going to go here, right, I'll connect my wallet again, this urgent, and if you look at this, this is approved. So we approve the spender, which will be the contract address here. So if we go back here, this is the contract address. We can copy it from this place. We approve the contract address, a spender, to be able to spend any amount we want. So in this case, let's just say this number, and then write, and then confirm. So with that, this contract can be able to, deposit funds into the vault. Again, because now the contract which we just deployed is approved to spend money from the caller. So if we do this and then write, you see this works. You confirm, okay, and then the transaction should have gone through. So if you follow this link here, we would see, accepted on L1, received, accepted on L2, and yeah, this pending, accepted on L2. So this is being accepted on L2. If we want to confirm that, we can go and check the balance of the account. So the account is the caller again, so there's the contract address here. So if I paste this here, you see that this has 100. So we've been able to deposit that amount of ETH to the caller. And again, you say 100, we only have one ETH, right? You see that we only have one ETH. So again, ETH is in 18 decimal places on Starknet. So if we check this, I believe, okay, if we check this, I will check the right read. I believe you can see if you query it, it's in decimal places. So yeah, it's just that. So it's 0.00000 something, each that's been sent to this vote, and now anybody can, deposit into this vote. There's other things you can do to it, right? You can have a permission vote that only whitelisted, accounts can deposit to the votes. You can, maybe have it that the funds deposited to this vote is kind of deposited to, maybe a yield generating platform. And we can explore this like in more advanced lessons, but yeah, this lesson was just to show you, the implementation of a simple DeFi vote, and I believe, we've gone through that. Again, you should be able to define and declare a contract interface. So again, we use the trait, and this pub keyword is just, make it publicly accessible, or make it publicly accessible in the contract, within a contract that we're using here. Or the project. Again, we have the mod. So the contract is just a model in Starknet, and we have to define this attribute here. We have the storage. So every contract needs a storage, right? We imported some dependencies, and in this case, we got the get caller address, get contract address. We had the storage. We imported this from the Starknet standard library, this, and the contract, again, just like, why can't we just use it here? We can, but we already defined it here, so I just kind of pulled it back in. The constructor, again, this is a function that runs once the contract is deployed. So at deploy time, this runs, and you cannot run it again, after it's deployed. These are the private functions. Again, we did not mark it as, public. And this one, we specifically said everything defined in this, implementation is public. So all the functions here are accessible. So the deposits, the withdraw, and again, we had a ref self. So we say we're going to be modifying the state. So this made this function a write function. And again, we had a self and taking a snapshot, which means we're not modifying the state of the contract. And so we can read from it. But yeah, this is a simple DeFi Vault implementation. We've deployed it and we've deposited to it. Next lesson, we're going to be going over like writing tests for a simple DeFi Vault.